We've seen how to differentiate trig. Now let's see how we go back the other way and integrate trig. And it is simply that, we're just going back the other way, so it's the reverse of what we've seen. But we really got to be careful because of the negatives. This is where you can easily make a mistake, because remember, to integrate cosine, it'll actually go to positive sign. Right? Whereas when you differentiate cosine, you go to negative sign. So you've got to be very careful. And I've just put up a linear function here. So if it is a linear function, a bit like the exponential where we saw you just go 1 on a out the front, similar here, 1 on a sine ax plus b. Sine now would go to negative cosine. And, well, we won't have tan, but we'll have sec squared. Sec squared will go to 1 on a tan. Now remember, if you're ever unsure, those three will be on the reference sheet, so you can always check and make sure you got it the right way around. So we get sine 3x, integrate that, so sine goes to negative cosine, so we've got minus a third cos 3x, plus of course a constant. Cos of 1 minus 5x, oh, here we go. Cos goes to sine, however, the coefficient of x is negative, so when I go 1 over a, I will get negative 1/5 sine of 1 minus 5x. This is what I'm saying, I'll be really careful with our negatives. So easy to make a silly mistake there. Sec squared, well, the reciprocal of a half is 2, so we get 2 tan. So they're the sort of very basic ones. I suppose if they ask us those questions, we say, thank you very much. Let's do a definite one. Sine of 2x, so that it becomes minus a half of cos 2x, and we're going from pi on 6 to pi on 2. Remember, it's always radians, so even if those numbers don't have a pi, that we were just talking about there, they are in radians, we would assume. Unless, of course, they put a degree symbol on it. Now, if they put a degree symbol on it, then we know they're saying degrees, but we still need to substitute in radians. Although, actually, now I think about that, it wouldn't matter, would it? Because we're substituting it into the cosine function. As long as your calculator matched what you were subbing in, it'll be okay. It's only if our answer was something like x cos 2x, then that would matter. So, yeah. All right, anyway, let's sub in. We get the cosine of pi minus You'll see these exact values cropping up all over the place. So pi, I don't know, I still look at it and in my head go, oh, pi, that's 180 degrees. So cos of 180, cos of pi is negative 1, isn't it? We start at 1, go down, negative 1. And pi on 3 is the same as 60 degrees, so that's a half. So minus 1 minus half, all of that times minus a half, we get 3/4. Let's do a volume question. Volume of solid form when y equals the square root of sine pi x between x equals 0 and 1 rotated about the x-axis. So remember, pi times integral of y squared dx. Oh, how convenient. It was y equals the square root. So when I square that, the square root goes away. Wow, that was lucky. Just brilliant how that works out. Pi, of course, is just a constant number like any other constant number. So we know when we integrate sine, it goes to minus cos. So we'll have pi times minus 1 on pi, cos pi x. So the pi's cancel. Sub in the 1, sub in the 0, cos pi, which is negative 1, minus cos 0, which is 1. So minus 1, minus 1. Get all those minuses cancelling. We end up with 2. But it is a volume we're talking about. Units cubed. That's cubed. Here's a more interesting one. The integral of x, because all of those were linear functions. Now what if it's not a linear function? We do it exactly the same as we did with the exponentials. We want to create what we know. We know that we would like derivative times the trig function, and the function is the angle. So x squared, we would like 2x there, not x. So I can balance that out by putting a half out the front, and we know 2x sec squared x squared would then go to tan of x squared. So we get half of tan x squared plus a constant. Most of the functions do tend to be linear functions. Extension 2, of course, might be a little bit different. Extension 2 integrals, but we'll see all sorts of wonderful integrals we're going to end up doing there. Oh, integral of sine squared. Now this is where last year when we looked at double angles, I said, oh, remembering these double angle formulas, the rearrangement for what's sine squared and cos squared, that'll become really important next year. It's now next year. Okay. Because the sine squared, using my double angle, remember cos 2 theta, we can write it as cos squared minus sine squared. Although more useful for this one, we could rewrite it as 1 minus 2 sine squared. Rearranging that, I get sine squared as a half of 1 minus cos 2 theta. The other one was, of course, 2 cos squared theta minus 1. Rearranging that, we got cos squared half 1 plus cos 2 theta. So they're basically very similar. It's only the sign that's different. So cosine has the plus cosine. I suppose match it up, cosine with cosine. Sine is different, so we change the sign there. Maybe that's one way of thinking about it. So the minus goes with the sine squared. So this is a sine squared, so we'll get a half of 1 minus cos 2x. And we can integrate those quite easily. So the 1 will just go to x. Cosine goes to positive sine, but it's minus times that, so we've still got the negative there. 1 over 2, which is a half, of course. Whether you leave it factorised, whether you expand it out, I suppose it doesn't really matter. But there's our answer. They love asking that question or a variation of it. I think last year it was, I should remember this, I marked it. I think it was either sine squared or cos squared of 3x. So, you know, it's a very standard sort of question, you'll see. Ooh, integral of tan. Now, you will end up memorising this. It's not on the standard sheet, but you will see it quite often, especially in extension 2. You will end up memorising this. And it came from, we saw it yesterday. I did a differentiation question, sort of gives us a clue. If I rewrite tan x as sine on cos, I then have the situation of derivative on function. Well, almost derivative on function. Because of course the derivative of cosine is minus sine. So I'd like minus sine to be on the top. So let's balance it out. It means I have minus out the front. So derivative on function, it's a log when I integrate it. So we get minus the log of cos. Personally, I don't remember it that way. I remember it as the log of sec. So we can use your log laws, bring the minus in. So we're saying cos x to the power of minus 1, or the reciprocal of cosine, which is sec. Again, doesn't really matter. I just think it looks neater with a positive rather than a negative out the front. So. But both answers are, of course, identical. But having said that, you don't waste your time going, oh, that's sine over cos, da 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 da. You see integral of tan x, you just write, oh, that's log of sec, or minus a log of cos, whichever you prefer. Much like if you see the integral of log x, now you might not know it yet, but you will end up going, oh yeah, that's just x log x minus x. We will see how we get that later. Cos x times sine to the power of 7. Now you might not see it straight away, but this is in the form of derivative times the function to some power. So it's one of those sorts of questions. The function in this case is sine. So, and the derivative of sine is cosine. So we do have the derivative times the function to the power, so I can just add 1 to the power over the power. Now if you don't see it straight away, you could use the idea of substitution. I could say, oh look, if u was sine x, then du would be cos x, differentiate sine and get cos, and I can say, oh hang on, I can rewrite this. But of course then I would have to change the limits as well, because now if I'm changing the variable, pi on 2 and 0 are no good to me, although 0 still works, because when x is 0, u would end up being 0. But when x is pi on 2, u is the sine of pi on 2, which is 1. And so I could just rewrite the integral as u to the power of 7 du, add 1 to the power over the power, substitute in 1, minus substitute in 0, an 8. as I think it's a lot quicker if you do recognise the pattern and you see it and you say, oh, yes, it's in the form derivative times function to the power, so I can just add 1 to the power over the power. So you would have gone, oh, well, that's 1/8 sine to the power of 8x, and then just sub into that. Just saves a little bit of time. But again, it doesn't matter, either way it works. Okay, let's spend the day playing with our integrals. 14J.